Okay, so the focus today is really picking the best method to find the volume of a region. So we've done the solids of revolution now using the disk and washer method, and we did cylindrical shells. So today we're going to look at the region where we're rotating and decide which method is going to work the best. And hopefully by the end of this video you'll kind of see I'm doing these 4 parts here to this problem, and we'll see with doing those parts what is the best method. So the first step, as always, is to sketch a graph of what we're rotating. So we've got this, and we've got 4 minus x for y, so we start up here at y equals 4 and go down here, and then we do y equals x, and then we've got the line y equals 4. So we got this little region up here, and this is what we're going to be rotating in each part of the problem, except we're rotating about different lines. So for part A, and let me go ahead and put these points down. This is 2, 2. This is 4, 4. And this point is 0, 4. Alright, so the first part we're rotating about the x-axis, which is down here. And we need to decide whether we're going to use washers, disks, or the shell method. Now, right off the bat, since we're not touching the x-axis and we do not have a nice thing touching the x-axis, and I want you to notice we don't have a nice bottom bound for the whole thing. We have a nice top bound, but the bottom changes from as we go from left to right. So we're not going to use disks at all. Alright, and since I don't change nicely from my functions and I'm rotating about the x-axis, I could, if I was going about the y, I could use the washer method, and we'll see that in part B. But since I've got this nice space down here and I'm going about the x-axis, cylindrical shells actually make the most sense here. Alright, now a couple things. When we're doing the shell method, we're actually going to integrate with respect to y on this one, because when we look at these pieces here, I've got a nice height from left to right, and I've got a nice radius from the x-axis out to that piece. So my radius is going to be like this, I thought I switched to blue, but I guess I didn't. So this is my radius here to that height. So I do have nice things like that. So that's why I'm going to pick shells here. So for my shell, my radius is going to be my distance from my x-axis, which in this case is just y. And then my height, I've got to remember a couple things. This second line here is x equals y if I rearrange it, and I've got to take away the other part, so I have to switch this x and y around here, and I get 4 minus y. So in this case I end up with 2y minus 4, and my volume integral is going to look like this. We've got 2 pi. I'm going from 2 up to 4. I've got my radius being y, and I've got my height being 2y minus 4, and I'm integrating with respect to y. Alright, so we'll go ahead and distribute that y in, and we get 2y squared minus 4y dy. And you do your antiderivative, and we find our volume can be given by 2/3 y cubed minus 2y squared. And we're evaluating from 2 to 4. And through some handy dandy math magic that I've already worked out, that should end up giving you a 80 pi over 3. So I'm not going to show all the steps on how I got that answer. You can work that out and verify that on your own if you'd like. Alright, let's move on to part B. So this time we're spinning the same region about the y-axis. So in this case we're going, here's the y-axis, we're going around this way. Now, we got to decide again, are we going to use washers, discs, or shells? Since we've got these two lines that change the distance away from the y-axis, it's actually going to be the best to use the washer method in this case, because we'll have a little radius to this line and we'll have our big radius out to this line being the capital R. So it's actually best to integrate with respect to y and use the washer method, since if I try to do shells, our radius varies. See how the radius varies? Since we have those two things and we're varying our radius between the y-axis, we have two different functions there. It's actually best to use washers. So we're just going to use the washer method here. And if you remember, that's the volume is like this, where we have pi times the big radius squared minus the little radius squared. And in this case we're going to do with respect to y, so I'll put the dy there. So our little radius, our big radius is x equals y. So our integral is going to be from 2 to 4 like we did before, because our y values go from 2 up to 4. So we're going from 2 to 4. And we're going to put the pi out front. And we're going to do our radius, our capital R, is equal to y in this case. So we're going to do y squared minus, and our little r in this case is going to be our 4 minus y. And we're going to minus 4 minus y squared from y squared. And if we evaluate this integral, that will give us our volume. So let's just do some simplifying here. We got y squared, and then we're going to have 16 minus 8y plus y squared from that. And our volume integral looks like this now. We're going from 2 to 4. And we'll do y squared minus y squared. That goes away, so I'm left with negative 16 plus 8y. And that gives me pi times my antiderivative, which is negative 16y, plus, and then I do y squared, and that means I got to do half of 8, so 4, and we're evaluating from 2 to 4. I'm not going to show all that work out here, but that should give you the volume being 16 pi at the end. So again, in this case it was easier, it was necessary to do washers because of the way the radius changes. Since I have those two separate radii and we're spinning about the y-axis, I chose to do washers.
Excuse me, all English.
So this time we're rotating about x equals 4. And again, in this case, the region I have with a vertical axis of rotation, I end up having to do washers again. Alright. Except this time my little r goes there and my big R goes to this side of the function. Alright. So to do that, my little r, I take 4, which is my x value, minus y. So again, we're doing this with respect to y. My capital R is going to be 4 minus y. And that actually just ends up being y. And then I do my volume. Again, when you see this integral, you'd be like, oh, that looks just like the last part. That's because we're taking the region and we're rotating it about the other side, so it should be the exact same volume as what we had before. And in this case, we get the exact same integral as what I had in the last step, so I'm not even going to work that out again. We know that it's 16 pi. Alright, so we're revolving around the opposite end where the 4 is, whereas before we had it around the y-axis. So again, we just pretty much flip-flop our radii in this case. So before we had over here, again, my overall radius is 4, and then when we had it the other way, from x equals 4, my overall radius for the top part is 4 every single time. So hopefully that makes sense that this is the same volume as the last time. So I was mostly just showing you the setup there. So, and then one last one. We have the same region, except this time we're revolving around y equals 4. So y equals 4 is our axis of rotation. And again, for this one, I chose to do the shell method because of the situation. We're rotating around a horizontal axis. We got a nice way to define a top and bottom piece here, or a left and a right piece, being right side, left side. So we can actually do our radius. Since I've got this 4, my radius is going to be 4 minus y. So there's my radius. My height is a nice function this way of x, or of y, between those two pieces. So my height is going to be my right side minus my left side. So in this case, my right side is y, my left side is 4 minus y, which is 2y minus 4. And I just got to set up my integral now. So I'm doing from 2 to 4 of 2 pi. So this is my volume. 4 minus y times 2y minus 4. Alright, and we multiply that out, we get our 2 pi out front, 2 to 4, and we get negative 2y squared plus 12y minus 16, and we're integrating with respect to y. So that's 2 pi, and then we do our antiderivative, so that's negative 2/3 y cubed plus, and then I got to take half of 12, so I got 6y squared minus 16y, and we're going between 2 and 4. And if you work this out, your volume should be equal to 16 pi over 3. So again, it's pretty much you look at the region that you have and the axis of rotation, and then decide, do I have a nice clear left bound, right bound, or top bound, bottom bound for the function? Can I do a height and a radius, or do I just need to do the 2 radii, subtract it to do the washer method? Again, it varies by problem. You gotta get yourself a good sketch of the situation, and then decide from there where to go.